You think you understand speed, don't you? You've been in a car. You've seen a plane fly overhead. Maybe you've even felt that push in your chest when something accelerates fast. Speed is simple. You want to go faster? You push harder. More power, more speed. That's how it works. Except it doesn't. There's a wall, a barrier built into the universe itself. And no matter how hard you push, no matter how much energy you have, you can't break through it. 299,790,458 meters per second. That's the number, the speed of light. But why? What makes that number special? Why can't you just build a bigger engine, gather more fuel, push harder? Most people accept it without thinking. Einstein said so. That's the rule. But that's not understanding. That's memorizing. When you actually dig into why there's a speed limit, when you really ask what stops you, we find something so strange that it rewrites everything you think you know about motion, about time, about reality itself. Let me show you. Start with Galileo, 1638. He's dropping things off towers, rolling balls down ramps, timing everything carefully. He discovers something remarkable. When you drop something, it falls faster and faster. It accelerates, and the acceleration is constant. Drop anything, a rock, a ball, a book. In the first second, it falls about 16 feet. Doesn't matter what it is. Doesn't matter how heavy. 16 feet in 1 second. That was revolutionary. Before Galileo, people thought heavy things fell faster. They were wrong. Galileo measured it, teamed it, proved it. Everything falls at the same rate. Now jump ahead. Newton, 1687. He's thinking about the moon. The moon goes around the earth. Why doesn't it fall down? What keeps it up there? And then he realizes something brilliant. The moon is falling. It's falling toward earth constantly. But it's also moving sideways fast enough that it keeps missing. Think about it. If you throw a ball horizontally, it curves down and hits the ground. Throw it faster, it goes farther before hitting. Throw it fast enough, and the curve of its fall matches the curve of the earth. It never hits the ground. It goes around. That's an orbit. Falling and missing. Over and over. Newton calculated how far the moon should fall in 1 second if gravity weakens with distance. He used an inverse square law. Twice as far away, gravity is 4 times weaker. 3 times as far, 9 times weaker. The moon is about 60 times farther from Earth's center than we are. So gravity at the moon should be 60 squared, 3,600 times weaker. On Earth, things fall 16 feet in 1 second. At the moon's distance, with gravity 3,600 times weaker, the moon should fall about 1/20th of an inch per second. Newton did the calculation. It matched perfectly. The moon falls at exactly the rate his law predicts. Disconnected two completely unrelated things, falling apples and orbiting moons. Same force, same law. Universal. Now, Newton's laws got tested. Constantly. Astronomers watched the planets, watched the moons of Jupiter. And here's where it gets interesting. In the 1670s, old Rømer is watching Jupiter's moons, timing when they disappear behind Jupiter, timing when they reappear. He's making predictions. This moon should reappear at this exact time, and he's checking, and something's wrong. Sometimes the moon reappears 8 minutes early, sometimes 8 minutes late. 8 minutes. That's huge. Something's off. Other astronomers thought maybe Newton's law was wrong. Maybe gravity doesn't work the same way out at Jupiter. But Rømer noticed a pattern. The moons appeared early when Earth was close to Jupiter. They appeared late when Earth was far from Jupiter. And he had a wild idea. What if light takes time to travel? What if we're not seeing the moons as they are now, but as they were some time ago? When Jupiter is far away, the light has farther to travel. So we see things later. He calculated how much delay there should be based on Earth's distance from Jupiter. And from that, he worked backward to find the speed of light. About 220,000 kilometers per second. Not quite right, but close. The first measurement of light's speed, and he got there not by measuring light directly, but by trusting Newton's law of gravity. When something didn't match, instead of throwing out gravity, he asked what else could explain this. And he found the speed of light. This is how science works. One discovery leads to another. Each insight opens doors. So now we know light has a speed, about 300,000 kilometers per second. Fast, but not infinite. For the next 200 years, people measured it more carefully, using better techniques, getting more precise numbers. And then, in the 1800s, something strange starts happening. James Clerk Maxwell is working on electricity and magnetism. Completely different topic. He's writing equations that describe how electric and magnetic fields behave. And when he solves those equations, he finds that electromagnetic waves should exist. Waves that travel through space at a specific speed determined by two constants, the electric constant and the magnetic constant. He does the math. The speed comes out to about 300,000 kilometers per second. Wait, that's the speed of light. Maxwell realizes light is an electromagnetic wave. That's what light is. Oscillating electric and magnetic fields propagating through space. But here's the key. The speed isn't arbitrary. It falls out of the equations. It's determined by fundamental properties of empty space itself. Space has an electric constant. Space has a magnetic constant. Those two numbers together determine how fast electromagnetic waves travel. And that speed is the speed of light. Now people start testing this more carefully. And they find something absolutely bizarre. The speed of light doesn't change. No matter how you measure it, no matter how fast you're moving. This shouldn't be possible. Imagine you're on a train moving at 100 kilometers per hour. You throw a ball forward at 50 kilometers per hour relative to you. How fast is the ball moving relative to the ground? 150 kilometers per hour. You add the speeds, that's obvious. Now replace the ball with light. You're on a spaceship moving at 100,000 kilometers per second. Half the speed of light. You shine a flashlight forward. The light should be moving at its normal speed, 300,000 kilometers per second, plus the ship speed, 100,000 kilometers per second, plus the ship speed, 100,000 kilometers per tempered second, total 400,000 kilometers per second relative to someone standing still. But that's not what happens. You measure it. The light is moving at 300,000 kilometers per second. Exactly the same as if you were standing still. People tried everything. Different directions, different speeds, different ways of measuring. Always the same answer. Light always travels at the same speed relative to you, no matter how fast you're moving. This broke physics. It didn't make sense. It violated everything about how motion works. Albert Einstein is thinking about this in 1905. He's 26 years old, working in a patent office, and he realizes something profound. Everyone is trying to explain why the speed of light stays constant. They're inventing weird theories about ether wind and length contraction. But Einstein takes a different approach. He says, what if the speed of light being constant is the fundamental fact? What if that's just how the universe works? And everything else, space, time, motion, has to adjust to make that true. That's a radical shift. Instead of explaining the constant speed of light, accept it as fundamental and figure out what that implies. And what it implies is shocking. Time is not absolute. Time runs at different rates depending on how fast you're moving. Space is not absolute. Distances change depending on your motion. If the speed of light must be the same for everyone, then time and space have to be flexible. They have to stretch and compress to make the math work out. Einstein works through the math. He publishes a paper, Special Relativity, and it predicts all kinds of bizarre things. Moving clocks run slow. Moving objects shrink. Mass increases with speed. Time and space are interchangeable. At first, people think he's crazy, but then they test it. And it's all true. Every prediction, confirmed over and over. Joseph Hafele and Richard Keating do an experiment. They take 4 atomic clocks, the most accurate clocks that exist. They synchronize them perfectly. Then they put 2 clocks on commercial airplanes. One flies eastward around the world. One flies westward. The other 2 clocks stay on the ground. When the planes land, they compare the clocks. The clock that flew eastward is behind by 59 nanoseconds. The clock that flew westward is ahead by 273 nanoseconds. Nanoseconds. Billionths of a second. Tiny, but measurable. And exactly what Einstein's equations predict. The planes were moving fast enough that time dilation became measurable. Time genuinely ran at different rates for those clocks. This isn't theory. This is measured. With clocks on airplanes. GPS satellites do the same thing. They're moving fast, and they're in weaker gravity, so time runs differently for them. About 38 microseconds per day different. If we didn't correct for that, GPS would be off by kilometers within hours. We correct for it not because we believe Einstein. We correct for it because time actually runs at different rates. Particle accelerators prove it even more directly. At CERN, at Fermilab, at other labs around the world, we accelerate particles to incredible speeds. Electrons, protons, even heavy ions. The closer we get to light speed, the more energy it takes to go faster. Not because of friction. Not because of inefficiency. Because the particles are getting heavier. At 86% light speed, a particle is twice as massive as at rest. At 99.5% light speed, about 10 times as massive. At 99.99% light speed, about 70 times as massive. We don't just predict this. We measure it. We have to design the accelerators to account for it. The magnets that steer the particles have to be stronger, because the particles are heavier, and no matter how much energy we pump in, we can't get the particles to light speed. We can get to 99.99999%. We can get arbitrarily close, but never quite there. The energy required approaches infinity, which doesn't exist. So we hit a wall. Carl Anderson discovered antimatter in 1932 by studying cosmic rays. High-energy particles from space hitting the atmosphere. Some of those particles create muons, unstable particles that decay quickly. Average lifetime 2.2 microseconds. In 2.2 microseconds. In 2.2 microseconds. Even moving at nearly light speed, a muon should only travel about 660 meters. But muons are created in the upper atmosphere, about 10 kilometers up. They should all decay before reaching the ground. Except we detect tons of muons at sea level. Why? Because they're moving so fast that time dilation is extreme. From our perspective, they live longer. From their perspective, the atmosphere is contracted, shorter. Either way, they reach the ground. And the number that reach matches Einstein's predictions exactly. So why is the speed of light the limit? It's not about light. Light just happens to travel at that speed, because photons have no mass. The real answer is deeper. Einstein showed that space and time aren't separate. They're woven together. Spacetime, a 4-dimensional fabric. And spacetime has a structure, a geometry. And that geometry has a built-in conversion rate between space and time. You can trade motion through time for motion through space. But the exchange rate is fixed. 300,000 kilometers per second. The speed of light. When you're sitting still, you're moving through time at maximum speed. 1 second per second. When you start moving through time at maximum speed, when you start moving through space, some of your motion through time gets redirected into motion through space. Time slows down for you. The faster you move through space, the slower you move through time. At light speed, all your motion would be through space. 0 through time. Time would stop. You can't go faster than light because you can't have less than 0 motion through time. That's the limit. That's the wall. Hermann Minkowski, Einstein's old math professor, figured out how to visualize this. He invented space-time diagrams. 4 dimensions, 3 of space, 1 of time, and on those diagrams, light always moves at 45-degree angles. That's what it means for light to always travel at the same speed. The geometry of space-time makes it work, and that geometry has consequences. As you approach light speed, your mass increases, your length contracts, your time dilates. These aren't optical illusions. These are real changes in the geometry of space-time. John Wheeler, one of the great physicists of the 20th century, said it perfectly. Space-time tells matter how to move. Matter tells space-time how to curve. That's general relativity. Gravity isn't a force. Gravity is curvature. Mass warps space-time, and objects follow those curves. The more mass, the more curvature. Near Earth, slight curve. Near the Sun, more curve. Near a neutron star, extreme curve. Near a black hole, so much curve that light can't escape. Why? Because inside the event horizon, all paths lead inward. To escape, you'd need to go faster than light. And you can't. The speed of light being a limit isn't just about motion. It's about causality. It defines which events can influence which other events. It's the structure of reality itself. So let's bring this full circle. Galileo measured how things fall. 16 feet in 1 second. Newton connected that to the moon's orbit. Same force, same law. Rømer used Jupiter's moons to find the speed of light, about 220,000 kilometers per second. Maxwell found that light is electromagnetic waves, and the speed is built into the structure of space. Einstein realized that the constant speed of light means time and space are flexible, and he built relativity from that. Haufele and Keating proved it with clocks on airplanes. Anderson found cosmic ray muons that live longer because of time, dilation. Thousands of experiments at particle accelerators confirm it daily. Each discovery building on the last. Each insight opening new doors. That's science. That's how we learn. Not by accepting answers. By asking better questions. Why is the speed of light the limit? Because space-time has a structure. Space and time are interchangeable through a fixed rate. That rate is the speed of light. You can't exceed it because exceeding it would mean moving backward in time. Cause and effect would break. Reality would fracture. The universe prevents that. Not as a law, as geometry. And understanding that, really understanding it